Hello and welcome back to Let's Code Physics. We are continuing our development of a rope physics simulator. This is an important topic in a lot of video games or a lot of simulations where you have, an extended object that can drip down, that can, have one end pulled or both ends pulled, one end fixed, both ends fixed, or various points fixed. The way we're going to model such a rope is with a series of atoms. Last time we worked with just 3 atoms, one that's stuck in place, one that's in the middle, one that's at the end. And we're modeling these atoms as being connected by springs. I have changed the visual on the spring to make them hopefully a little more visible. They were a little bit thin and darkly colored last time, so I've made the springs thicker and given them a white color now. And this thing is swinging back and forth, kind of like you might expect a rope to. Also importantly, last time we confirmed that the total energy of this system is conserved, very important for a physical scenario, for the total energy to be conserved. And this is working out well, but we've had to sort of manually create each of the atoms and each of the springs and then manually work out the formula for each of them. If I wanted to add a 4th atom, if I wanted to add another string or rope mass element on the bottom, I would have to go in and add more lines of code. And if I wanted a 5th, I'd have to go in and add more. The code would just get longer with the number of atoms, even though it's really doing the same thing over and over again. So for each of these atoms, it has to create the visual, it has to define the position, it has to create a spring. The spring's really there more for visual purposes than any actual physics. And then in the loop, for each pair of neighboring atoms, or for each spring, if you will, it has to calculate the force, meaning it has to calculate the vector for the spring, the direction along which the force is going to point. It has to calculate a magnitude, it has to calculate the unit vector, which is that length vector divided by its magnitude. Then it has to calculate the difference between the length of that stretching minus the natural length of the spring. And then it calculates the actual force using Hooke's law, and then it adds all those forces together for each atom. So each atom is going to have at most 2 spring forces, one from the spring above it, one from the spring below it, and a gravitational force, the force of its own weight, pulling it down. And so it's really doing the same thing over and over again. It just changes which element it's calculating the forces regarding. And so this is where a list is really handy. So what I'd like to do today is take this code that I've sort of put in one piece at a time and make it more list-based rather than individual object-based. So let's start from the beginning. The rope constants are all going to be the same. So each of these springs for right now is going to have the same stiffness and same natural length. That's what you would expect in a physical rope. But you might have a rope where, say, you've tied a rope, something nice and thick to a string, something a little bit thinner, and then you might get some different physics, something interesting happening in the middle, and we'll try that out a little bit later. But for right now, we're going to keep those constant across the rope, uniform across the rope. So interesting physics linguistic distinction. Constant refers to something doesn't change with time. Uniform means something doesn't change with position. It's a little bit of vernacular there to throw your way. So what I'm going to do is I'm going to end up creating a few lists. I'm going to have a rope list. And I always like to initialize my lists with zeros. VPython starts counting lists at 0, which is a little bit counterintuitive to us. So I just make the first element 0, and then I just append all the other elements. And we're going to have a spring list. So this is going to be the list of atoms in the rope. And this is going to be the list of springs connecting the atoms. Cool. So what I'd like to do now is I would like to have each of these, where I've been defining these individual things, I'd like to have them be, instead of giving them their own variable names, to just add them onto the rope list. So we would call this rope list.append. And so what it's doing now is I'm telling the code, I want you to create a sphere that has all these attributes, just like the top ball had before. Only now, instead of giving it an individual name, I want you to give it rope list. I want you to put it as the next item on the rope list. And then I can do the same thing with the middle ball here. I can say rope list.append, etc., etc. Except even there, I'm having to Except even there, I'm having to create them individually, right? It would be nice if I could just tell the code, I want a rope of 20 atoms, or I want a rope of 30 atoms. And so what I'd like to do instead is set this up inside a loop. So let's have the in atoms equal to, let's see, we've already got 3 working out well. Let's bump it up to 5 just to be somewhat secure. So actually, now that I'm thinking about it, let's change this name from rope list to atom list. That'll make more sense because this is the list of the atoms. Okay. And so what I'd like to do now is I'd like to get a counter. So we'll start with n equals 1, and then we'll just loop over in going from 1 to the number of atoms. Cool. And so now what I can do is I can say, okay, now I want you to take this rope list and append another sphere to it, append another atom to it. Except again, I'm having to, here I've manually created the position. I don't want those positions to all be the same, so I need a way to sort of encode the position into the loop itself. So here's what I'm going to suggest we do. Let's do this. Let's create something called a, so I want to think of this in terms of the rope is going to be at a certain angle. Let's just start with the rope hanging at a certain angle, maybe from the vertical. So 0 degrees would be straight down, 30 degrees would be like this, 45 degrees would be like this, 60 degrees would be like this-ish. So let's call it starting angle. And let's make that starting angle, let's start with 30 degrees. So let's see, that's 30 degrees. VPython understands radians, not degrees, so I need to multiply by pi. Oops, that's not pi. 14159. There we go. I slipped on my number keypad. I'm sorry. Divide by 180. There's pi radians and 180 degrees. Cool. And so what we'll do is we'll say that we want to do a little bit of trig to get this thing out by that much angle each time. And so what we'll do is we'll say that x is going to equal, let's go with n minus 1, because we do want the first one to be at 0, 0. N minus 1 times the rest length, meaning each rope segment is going to be the rest length long. And then I just need to multiply this by the sine of the angle. Starting angle. There we go. Should have given that a less complicated name. Oh well. And then we'll do the same thing for y. And this time we'll, but I need to actually name it y. So since I'm measuring the angle from the vertical axis, x is going to get the sine, y is going to get the cosine, although I want it to hang down, so we'll make y the negative cosine. There we go. And this is how I was raised to do coding, is to, if you can align something, to make it align. So now instead of having this 0, 0, I can say x and y, and it'll update this x and y value every time the loop goes around. And tell you what, let's start to make this thing a little bit less distinguishable between the atoms and the springs. Let's make this whole thing white. And then I don't have to keep adding more of them, which is pretty cool. Awesome. And so now I can get rid of all the rest of the sphere creation commands. And I also need to start giving these things velocities. So instead of having individual velocities, I now need a velocity list. I forgot to add that up here. So we'll call that vel list. And so that'll be the list, not listoff. Liz Toff, I'm sorry to have inadvertently written your name there. List of velocities of atoms. There we go. And we'll have them all start at 0 just for now. We'll change that a little bit later as we try a different scenario. Vel list dot append vector 0, 0, 0. So you're having a vector being an element of a list. So it gets a little bit complicated, but it's still fun. Okay, so I've got the ropes, I've got the velocities. Now the question is, how do I create the spring list? Because there's one fewer springs than there are atoms, right? So if I have a 3-atom rope, I've got a spring between these two and a spring between these two. So 3 atoms makes 2 springs. 3 atoms makes 2 springs. If I have a 4-atom system, I have a spring between these two, a spring between these two, and a spring between these two. So that creates a 3-spring system. So I think the way we'll do that is we'll go ahead and include that in this loop. And the way we'll do it is if n is greater than 1. Right, so if n is less than 1, it's not going to try creating 1. And so what we'll do is we'll create the spring the same way. In fact, I'm just going to delete this up to here and bring that spring command up to here. So we'll have the position of this thing be the current atom's position. So atom list of, that's going to be atom list of n dot pos. And we'll have the axis be atom list of n dot pos, so the current spring's position minus the previous spring's position, atom list in minus 1 dot pos. And that'll also, by having this under if n is greater than 1, in that first loop, n equal to 1, it's not going to try to subtract atom list of 1 minus atom list of 0, which there is no atom list, there's no atom in atom list of 0. Let's see, and instead of saying spring equals, I want to say, did I call it spring list? I did. Spring list dot append. Spring list, let's see. So I don't need the spring command anymore. I don't need the bottom velocity anymore. And so now you notice this has already become nice and cleaner. So I've only got the creating an atom once. I've only got the creating a velocity once. And I've only got the creating a spring once. So that's already nice and convenient. And so now what I need to do, that I've got the sort of initial setup taken care of, is I need to go into the loop and think about how I'm going to redo the loop. So again, before we were calculating all of this manually, one at a time. We want to automate the process now. So we're going to sort of recreate the loop we have up here. So we're going to start with n equals 1. And we're going to have while, oops, y'all almost let me forget this again. This has been the thing that I've forgotten in nearly every project, n equals n plus 1. If your project ever doesn't seem to be going anywhere, if your code doesn't ever seem to be going anywhere, make sure you incremented the counter there. I know I know there's probably a for loop in VPython. I'm sure there is. I just haven't bothered to learn it yet, and I'm lazy. That's why I program, is because I'm lazy. Right. So while, I'm just kidding. Programming is very hard work, right? So while n is, you know what? I don't need to call that 5. I need to call that in atoms. Y'all have been staring at that for a while. So that way I only have to change that once, and I also don't have to change it here. So while n is less than or equal to number of atoms. Yes, good. So now we want to recreate this. We want to recreate this loop here. So what I want to have is, I want to have the length being between the two atoms, meaning this atom and the previous one. So I only want to calculate a spring force. Actually, let me think about this. No, I want to calculate the spring force starting with the first one. So this is going to be if n is less than the number of atoms. So I don't want to be calculating the force between the atom and the next atom when I get to the last one. When I get to number 5, for example, I don't want to calculate the force between it and number 6 because there is no atom number 6. I'll show you how we'll handle this in just a minute. And so what I want this to do is, let's see, this was last time between the middle and the top, and I was interested in evaluating the force on the middle. So I want this to be the sort of the first one. So let's make this one atom list of n dot pos minus, now we're going to go atom list n plus 1 dot pos. So now we're looking at the difference between them, meaning going from the current one to the next one. Last time we were going from the current one to the previous one because we hadn't created all of them yet. Now we do have all of them. So now we can go from the top, one and evaluate from there. Then we'll do the same thing here, calculating the L hat. We'll do the same thing here, calculating S. And then we'll do the same thing here, calculating F spring. So negative Ks times S times L hat. Okay. So here's where I want to think about this is, so most of the atoms, nearly every one of the atoms is going to have 3 forces acting on it. It's going to have the force from above, meaning the force from the previous spring. Where's my force calculation? There it is. Each one's going to have the force from the previous spring, the force from the next spring, and the gravitational force. Nearly every single one of them is going to have that. They're all going to have it except for that top one and that bottom one. So I need some way of keeping track of the force that I just calculated on the previous pair. And so what I'm going to do is I'm going to create a new variable. We're going to call it F previous, meaning the previous force. This is the force from the previous spring. And I'm going to set that equal to 0 to begin with. The reason I'm doing that is because when I get to that first atom, when I start out at the first atom, it has the next spring pulling on it, but it has no previous spring pulling on it. So I want to, so it's as if there is no spring, so there is no force. There is no spring. So I'm going to set that to be 0, so that way I can include that in the calculation and not have to worry about it the first time. So we're saying if in less than number of atoms, yes. All right, let's come out of that loop now. And what I can do is I can say that the, let's see, so I don't need this repeated anymore. I do need the gravitational force still repeated. I do want to check the energy, but I don't want that to be inside, I don't want that to happen inside the loop. And actually, I want this to go in one more. Okay, yeah. So now this is going to be the force inside there. There we go. They're the gravitational force calculated inside the loop. And I want to take this force calculation. And so this one is the force that was calculated for the spring plus the force of gravity. And we're going to say minus F previous. Oh, since I've got underscores elsewhere, let's put an underscore there. I'm going to put minus S previous because whatever force the spring exerted on the previous ball, on the next atom, it's exerting the same force but in the opposite direction. So if you just put a minus sign, that should take care of that. And then I can start incrementing my velocities. Oh, now here's where I run into an issue, is that I don't want to update the velocities and positions I don't want to update the positions just yet. I can go ahead and update the velocities, but I don't want to update the positions because that's going to change the calculation up here. So what we're going to do is we're going to update the velocity here, and we're going to say velist of n is equal to velist of n plus force divided by mass times dt. That's the same thing I have right here, right? Velocity equals velocity, meaning the next velocity equals the current velocity, plus force divided by mass times dt. Cool. So we're going to say update velocity. Cool. And here we'll say total force on atom. Cool. But I don't want to update the positions yet because the positions are still impacting the force calculations here. So what I'm going to do here is set up another loop. So we're going to repeat the loop basically. So while n is less than or equal to number of atoms, and then we'll do the then we'll have the position update. So we'll say atom list of n dot pos equals atom list of n dot pos plus vel list of n times dt. Right? That's what I have here. Right? Is position equals position plus velocity times time, change in time. Position equals position plus velocity times change in time. Cool. Update position. Cool. All right, so let's think through this. So when it comes in at n equals 1, it's going to have an F previous of 0. It's going to calculate the force of the next spring. It's going to add those forces together. This is not going to count for anything. Hooray. So as it loops through, that all works. When it gets to n being the number of atoms, when it gets to n equals the number of atoms, then I run into an issue because I don't want it to have this this F spring there anymore because there's no next force for it to calculate. And so I think the way we'll do that is we'll simply say if n equals number of atoms, then F... Oh, actually, there's an even easier way to do that. We can reset F spring equal to 0 here. And then I don't have to set up another if then. So it'll run through, it'll set F spring equal to 0, and then it'll simply say if n is less than the number of atoms, it does the spring calculation. If n has reached the number of atoms, then it doesn't worry about that anymore, and f spring will be 0. Cool. I think that's a little bit cleaner way to do that. Okay, cool. Now here's the thing. I also want to do an energy calculation. So let's do this. So let's incorporate the energy calculation into here. So we'll say energy equals 0.0. And then what we'll do is we'll add the energy for each one of these. So energy equals energy plus, and then I need the kinetic energy for each atom. So that's going to be 1/2 mass times magnitude. Now I'm looking at the vel list of n. And I need each one's gravitational potential energy. So that's going to be this thing. And instead of bottom ball, I just say atom list of n dot pos dot y. And then I also need the spring potential energy. And so what I'll do there is I'll go ahead and update the, let's go ahead and update the springs positions here. So I don't need this anymore. Well, I need the 1/2 k squared, but I don't know how to write that. I don't need any of these anymore, except I do want to copy the spring adjustments. So let's see. Tell you what, I think the best way to do that is going to be to put in another if command, or if block. So if n is less than the number of atoms, because again there's one fewer springs per atom, then I need to start updating these springs positions. So spring dot position, spring list of n dot position is equal to, this is going to be atom list of n dot position, because each one starts at the, I'll have them starting a little bit differently here. Tell you what, let's change this one to n less than n atoms just to make that match that one. So that way each spring is now associated with the atom above it, with the starting atom, not the finishing atom. I think that makes more sense. Oh, and in that case, I need to have n minus 1 to... Oh, actually, no, let's make this one n to n plus 1. I should have had the match from the beginning. My bad. Is that how I want to do that? No, that's not how I want to do that. I want to do that as n... Nope, I think nope, I do want to keep that as the other way. N greater than 1, and then this will be, yeah, let's just do a whole bunch of undos. Control Z, Control Z, Control Z, Control Z, there we go. All right, so I had it, okay, so I had it as, actually, I'm not even sure, oh, well, we'll stick with it. We'll go for, well, yeah, so we'll go head to tail, so we'll go from source to end. In less than 1. Oops, in greater than 1. That won't get you very many springs, now will it? So let's see. So we'll do the same thing here. If n is, oh yeah, we're already in that part. Equals atom list n dot pos, spring list of n dot axis. I'll be able to tell if this messed up and if I need to switch it pretty early on. Atom list of n dot pos minus atom list n minus 1 dot pos. I think I need to switch those, but I'm not sure. But what I can do then is instead of instead of having to recalculate all those s's and everything, I can just say energy equals energy plus 1/2 ks times magnitude of the spring axis, because the spring axis is just the length of the spring, which is what I want. Actually, oops. I don't know what I just hit. I thought I was hitting Control left. Oops. Let's see here. So I probably hit Alt or something. So actually what I want is, because that needs to be magnitude of that minus L0 quantity squared. So I have 1/2 k, and this is s squared. This is the same thing that this calculation was up here. Cool. So if n is less than n atoms, it goes through and updates the springs, and it always updates with the kinetic and gravitational potential energy. And then it'll plot the energy, and I can get rid of these. My t equals t plus dt. So we've really got the same code. So 20 minutes later, we've still got the same things happening in the code. It's just now we're keeping track of them through list items. And so here's where I run the code. And the first thing we're looking for is whether this energy is flat. The second thing we're looking for is whether it swings properly. The third thing we're looking for is whether those springs are well behaved. Let's find out. Oh, rope list is not defined. Oops, where did I use rope list? Oops, I didn't change that to Adam. Y'all have been yelling at me for the last 15 minutes about that. Let's make sure I don't have rope list anywhere else. Nope, F5. Oops, it does. Oh, right. I have to actually make the thing a vector, don't I? So let's search for F underscore. My bad. Vector 0, 0, 0. There we go. And same thing here. Vector 0, 0, 0. There we go. All right. F5. Okay. I have messed up something because it's not moving, but I've also set these incorrectly. So let's fix the springs first. Not sure why the thing... Oh, it's probably stuck here because I need an n equals n plus 1. I remembered it, didn't I? Yeah, n equals n plus 1. And I think I need one up here probably. Yes, I do. N equals n plus 1. And let's go ahead and change those springs. So this actually needs to be n minus 1 to the next one. And then let's do the same thing. This one, I believe that one's set up correctly. We'll find out soon enough whether that's set up correctly. And then we'll do the same thing here. N minus 1 minus n. There we go. Let's give that one a try. Oops. Int object has no atom list. Has no attribute pause. Line 67. Line 67. Spring list of n.pause. Atom list of n.pause. Integer object has no attribute pause. I don't have any integers there. Oh, n equals 1, right? I'm starting there. The only thing I think of is it's going to that first element, but that would be n equals 0. It hasn't had a problem. It didn't have a problem with any of the... It didn't have a problem with any of the positions before that. Spring list n.pause. Where am I setting up spring list? Spring list.append. N equals n plus 1. Let's do this then. Let's say print. I'm looking for n. Oh, and I need to not have that be an apostrophe. So I'm doing now is I'm putting in a print statement to tell me what value of n it's looking for just before line 67. F5. I'm looking for 1. Okay. And then it has a problem in line 68. Oh, I see. It's this n minus 1. Oh, right. So it is going down to the 0 mark then. All right, how did I avoid that up here? Because it didn't seem to have that problem up here. Oh, if n greater than 1. Oh, okay, yeah. So if I switch those that way, I need to have n greater than 1. Yes, okay. I don't think I need that print statement anymore. Let's find out. See, what was happening was going back to that 0 that I used to initialize it. Okay, index list index out of range on line 67. So maybe I still need this thing, F5. I'm looking for 2, 3, 4, 5. Index list out of range. So when it goes to the... Oh, it doesn't like the spring list there. But I can't have... Oh, okay. One more fix. Let's make this... See, the problem is it can't access the 0 and it can't access n atoms. So at some point I need to... I want to say subtract 1 from that, but that's not going to work. See, this is where the real programming challenge comes in, is because I've got all the physics worked out. Now I have to figure out how to actually get the counter to work. Let's see. Okay, so it's going 2, 3, 4, 5. So maybe Oh, okay. Let's do it the other way. Let's do it this way in atoms. But then let's have this be atom list n plus 1, and then this can be n minus n plus 1. I think will work. I think. Okay, awesome. It's not going anywhere. I don't know why it's not going anywhere, but at least they're set up correctly. And the thing is looping. Oh, it's probably not. It probably doesn't seem to be going anywhere because I have that print statement taking up some computer time. So let's comment that out. Let's try that again. Oh, right. Okay, so it appears to not be going anywhere because it's all falling down, because I set that it's basically all in free fall, and as free fall, it's just going to fall like this. So I have not recreated the initial one. What I want to do is I want to fix that first atom in place. I completely forgot about the physical scenario I was working on. I was so worried about the list and the ends and the index out of range. Yeah. I want to keep that top one fixed. The best way to do that is to say if n equals 1, then set the force equal to 0. Right? Because if I want that first one to stay fixed, I want there to be basically no force on it. So you imagine you've got it glued onto something, and so the net force on it is 0. So let's try that. There's an invalid syntax. Oh, so I actually see 2 mistakes. The first one is that needs to be a double equals to make it a Boolean. I even made a video about that, for crying out loud. And then this one needs to be vector 0, 0, 0. You can stop screaming at me about it being a vector. I know it's a vector. Okay. Oh my. What is happening to that first one? Why aren't they swinging? That I don't believe that's supposed to be happening. No, that's not a rope that I know. Oh, okay. You know what? I wonder if I need to flip the sign of this thing. Let's try that, because that could have been the top one pushing the second one away. Nope, it's just going down. And you can tell there's a problem because there's not conservation of energy down here. Oh my, okay, no, that did not happen last time. Okay, so I've got some bugs to work out here. N plus 1, because I'm starting at the first one, right? Oh, you know what? I never set up F previous to be anything. Oops. I never added that F previous needed to be F spring, did I? I don't think I did. Let's search for F previous. There's the first one. There it is in the calculation. Nope, I said I was going to do that and then I forgot to. Yeah, so I have to store the previous spring force in there. Okay, so I'm switching that one back to the way it was. F5. It looks like it's swinging. It's swinging! It's even got a little bit of a delay there. You see, ooh, we've got some curvature to it. That's so nice. Oh, look, it's swinging back. It's swinging back. It's bouncing a little bit, but it's not going to bounce too much because I've got that length set to initialize to be the unstretched length. Ooh, look at that. That's Jungle Hunt right there. And most importantly, though, you see that the total amount of energy is flat. Right, so this is the total energy curve that is flat. This thing is swinging back and forth. That is lovely. This thing is going really slow because it's having to update, now within each loop it's having to do 1, 2, 3, 4, 5 atoms worth of calculations. So let's actually, I can probably get away with decreasing the time step. And I'm just going to go ahead and add some zeros onto the rate. I don't know whether it's already maxed out. Oh, there we go. Well, that just looks cool, doesn't it? I can probably decrease the rate. That's actually a little bit too fast. Looks more like spaghetti than a rope. Okay, there we go. Cool. So now I've got it set up to where I can have a rope of any length of atoms. So I can have as many atoms as I want in this rope, and it's going to swing back and forth. And that's actually a little bit choppy. Let's maybe decrease this by half and then double this. So the speed was fine, but it was a bit choppy, which suggests to me I need to change the DT, the time step. Oh, look at that. That is just a nice rope bouncing back and forth. It's conserving its energy. Oh, this is such a well-behaved rope. Cool. So, but like I said, the best thing about this is that, well, first of all, the physics is correct, and that's always good. But the best thing about this is that I haven't had to manually create any of these. All of the springs, all of the atoms, all of everything is taken care of in those loops. And it's all set to happen within these loops of number of atoms. So all I have to do is change the number of atoms. So if I want this to be a more lifelike rope, if I want this to be more fluid, then guess what? All I have to do is change the number of atoms. So let's increase this thing to, oh, I'm feeling really well, no, let's be conservative first. Let's just double it to 10. And what I'm going to do is I'm going to cut the spring's unstretched length in half so that the total length of this rope is going to be the same as it was before, but now we're dividing it up into smaller pieces. And so we should see it be a bit more fluid, a bit more rope-like, if you will. Oh, there we go. There, it's swinging back and forth. It's got a little bit more bounce to it now, I see. Although I suppose what I could do is add in a calculation. I'm going to write this down right now. I'm going to add in a calculation of the total length of the rope to see how much stretch there is total. So let me write that down for myself for a note for a future video. Calculate total length of rope. Are y'all watching this? Because I'm writing stuff down. Just to double check to make sure that it's, you know, that that's being physical. So this is really cool. So this is the same total length that it was before, at least initially. But now it's got more springs to it. Oh, actually, I probably need to increase the spring stiffness too, don't I? Yeah, because if I increase the number of springs, then that decreases the total spring stiffness of the rope. That's right. There we go. Now it's a bit now it's staying at a bit more constant length. Yeah. So I will add that in. I'll see if I can come up with that off camera. So cool. So we've got a rope simulator now. We can make the rope however long we want. We can give it however many length elements we want, and this thing will continue on. So we're going to next time take a look at some different scenarios using this rope simulator. I'm going to pretty it up a little bit off camera. I'm going to see if I can turn this into just a single curve, so that way you're not seeing atom spring, but you're just seeing a curve like you would with a rope. And then we'll take a look at some different scenarios with it and see what kind of physics fun that we can have with it. So thank you so much for watching. I'll see you next time. Bye-bye.